Hi guys, I am Vibhu Jawa and today I will be presenting a presentation on accelerating topic modeling with rapids and BERT models. About me, I am a senior data scientist in Rapids, which is an open source project under NVIDIA AI, and I build open source GPU accelerated data science products. I write about my work fairly often on Medium and NVIDIA developer blog. So if you find this talk interesting, I suggest checking them out. And feel free to reach out to me via LinkedIn or GitHub. So, in this presentation, first we'll go over the topic modeling overview, then we'll go over the BERT topic algorithm, then we'll go over the BERT topic library, we'll go over rapids, and then we'll see how everything is put together and how you can accelerate BERT topic with GPUs using rapids. So, first of all, what is topic modeling? I like to think of topic modeling as the answer to the question, what topic, can be found in the set of documents I have. How I like to think about it. Let's say we have a bunch of emails. One can be, here's the agenda for our meeting on Friday. That feels like a project topic to me. Let's say I have another email that says, hey, I have attached the receipt of my travel expenses. That can come under, the expenses label. And why would anyone wanna do that? A common use case is, when you wanna analyze various product descriptions and customer reviews. Another one is, let's say you are working in Netflix and you wanna cluster different kind of movie genres together based on the descriptions that you have. So you can do that using topic modeling. And there are multiple such use cases, especially in the information retrieval world. So first, let's try to understand the BERT topic algorithm. That is how you can use BERT and topic modeling together. So BERT is embedding is commonly used for creating embeddings, and then once you have those embeddings, you cluster your documents, and then once you have clusters of documents, you create labels for it. Let's look at all of these steps into more detail. The first one is embedding documents. This essentially, we start creating embeddings using a sentence transformer. These models are great for many languages and great for, creating either document or sentence embeddings, and essentially have become the gold standard in natural language processing. The second step is clustering these documents. So once you have these embeddings, you can cluster these. But because embeddings are often in a very dimensional space, normal traditional clustering algorithms really suffer with the curse of dimensionality, and you don't get meaningful results. How you fix that is by using dimensionality reduction. A common technique used for that is UMAP, because it essentially preserves the local and the global structure of embeddings quite well. But you can also use HGB scan to cluster and reduce the embeddings so that you identify the outliers. Though we focus on these two algorithms in this presentation, the BERT topic library is very customizable. So you can use any kind of dimensionality reduction or clustering technique that you may deem fit. The another interesting part is creating topic representation. So step one, you create embeddings of your documents using some kind of a transformer model. Step two, you essentially created clusters using those embeddings. Now, but once you have clusters, what do you do with them? Like, because most of the data in our jobs and daily lives is unlabeled, and you often are stuck with unsupervised techniques, it's we essentially used TF-IDF to figure out what can be an interesting label. But TF-IDF only works, on a per document basis. But here you want to find it on a per cluster basis. So we use class-based TF-IDF. How you can develop a mental model around class-based TF-IDF is, imagine uh, each cluster, you essentially each cluster which contains a bunch of documents, you combine all those documents into a single document, and then you extract the frequency in that large single document which is composed of multiple documents. And thus you can use a traditional technique like TF-IDF, but just by modifying your input in a smart manner, you get labels of words that can fit the description of the cluster that you have. So, well, now let's look over the BERT topic open source library. As we covered, BERT topic is a open source, is essentially a topic modeling technique, and BERT topic library essentially is a suite is creates a wrapper around that algorithm. It supports guided, semi-guided, and dynamic topic modeling, and also provides really cool visualizations. Uh, it's a fairly popular library. It has like 3,000 stars on GitHub. Last month, it saw like 57,000 downloads. And since March, it saw like a quarter of a million downloads. And um, and we are seeing, and the library is seeing it more and more adoption as time progresses. Now, before we go into how we accelerated the topic using Rapids, let's try to understand what is Rapids. So Rapids is an open source suite of libraries that gives you the freedom to execute end-to-end data science pipelines entirely on NVIDIA GPUs. But why would you want to do that? Or let's try to understand the motivation of using GPUs end-to-end for your data science pipelines. For this, I think we need to understand how data processing has evolved over the years. So the world of data processing and data science started from Hadoop. In Hadoop, essentially, you used to query some data, write it to disk, then do some ETL and write it to disk again, and then use machine learning and then write it to disk again. And writing and reading from disk became a big IO bottleneck, and that's where Spark came in. Spark meant like you keep everything in CPU memory, so, and we saw like a 25 to 100x improvement in performance, as well as a reduction in the amount of code that you have to write. Then came traditional GPU processing, where you for the things that were really compute bound, you wrote some custom CUDA kernels, but for everything else, you relied on CPUs. But as we'll see in the this presentation, as well as in general, that's often some an approach which is not scalable for multiple reasons. One is the code becomes really rigid because you need specialized knowledge and need to maintain specialized code for CUDA, and try to understand how hardware accelerators work. And you often go from CPU to GPU and back from CPU to GPU, and it really limits the flexibility you have. But what Rapids offer is a solution to that. So essentially, you have the same code that you would have on CPUs, but essentially you just use a Rapids wrapper around it instead, and you get like a 50 to 100x improvement. So essentially, you have the same code, and you have language flexibility, and you can leverage the power of CUDA kernels that have been really optimized. And let's try to understand how Rapids plays a role in the open source and just the open source community around data science in general. So I firmly and sincerely believe that the evolution and the growth in data science that we have seen just comes down to how accessible and easy the open source maintainers have made it to use libraries like pandas for processing, scikit-learn for machine learning, networkx for graph analytics, etc. So essentially, you abstract away all the complexity and just allow a business researcher, a data scientist, and an individual to just focus on the problem at hand rather than figuring out a lot of how complexity around acceleration and actually make data science accessible and easy to all. So what Rapids did was it accelerates the commonly used open source frameworks by providing one-to-one API equivalents to those libraries. Like you have QDF, which is an equivalent to Pandas. You have QML for machine learning, which is an equivalent to scikit-learn. We have QGraph, which is an equivalent to Network X. And for deep learning, we have PyTorch, TensorFlow. They both are fairly flexible to use CPU and GPU backend. So let's just briefly go over some of these libraries. So as I said, when you go from pandas to QDF, most of the times all you need to do is change the import statement, and you can get like a 150x boost. From Spark to GPU, you get like a 10x boost. From scikit-learn to QML, you often, on average, can get like a 80x boost. And then from Network X to QGraph, you get like a 250x boost. So that's like often an multiple, often an order of magnitude or two of improvements that you see just by changing the imports that you made. Now let's try to understand how we use this power of Rapids along with the BERT topic like library to accelerate this topic modeling workflow. So at first we have a collection of documents. We first need to tokenize them to be ingested by a transformer. For this we use Rapids subword tokenizer, and then we use a deep learning model from sentence transformers, which uses PyTorch under the hood. And then we have document embeddings. From those document embeddings, we essentially cluster them using UMAP. This is again accelerated using QML.UMAP. Then we use HDB scan. This is again accelerated using QML.HDB scan. And then once you have the cluster of documents, you need to run TF-IDF. This also is accelerated using QDF and QML, which both have count vectorizer and TF-IDF transformer, as you have in scikit-learn. And then essentially we need to find maximum maximize candidate relevant score. This can be done using Numba and CuPy and the suite of open source libraries that we have. So first, let's look at the end-to-end benchmarks of each of these steps that I mentioned. So tokenization, when we compare it to the CPU version from HuggingFace, which is the standard that everyone uses, you can see like we get like a 569x speed up. Again, the API remains the same. All you need to do is call QDF or Rapids version of it. Then essentially deep learning, which is often what people think as the go-to workload for GPUs. But here you can see that yes, deep learning is accelerated by like a factor of 8x, but stuff like dimensionality reduction sees an improvement of 27x, which is actually the majority of the workflow here. Something like clustering sees like a 4.1x speed up, and even say TF-IDF sees like a 8x speed up. A topic representation sees like a 12.5x speed up. So what you see end to end, you get like a 14.2x speed up by majorly just changing import statements and moving just that stuff around. So let's look at so from an end-to-end perspective, the workflows that took over an hour on the CPU now only take 4.2 minutes on GPUs. And we are comparing against a meaty CPU to make the comparison fair. So just putting it all together, the embedding and the deep learning part of it, which uses BERT, is accelerated using PyTorch and GPUs and its GPU backend. The UMAP and HDB scan is accelerated using QML. And for the topic representation and clusters, we use class-based TF-IDF and MMR. So, so though you can use these individual components in on your own, but with bird topic, we also it's fairly easy to use the rapid versions of the library. So since the recent release of version 10.0, all you need to do is you know provide the relevant QML model for dimensionality reduction or clustering, and you can just see 12x speed up out of the box by just providing these two statements. I would really want to acknowledge the work that Martin did for maintaining Bird topic, and also would recommend seeing his NLP talk on topic modeling, by combining old with the new. Also, I'd like you to introduce you to some relevant links on this topic. One is Accelerating Topic Modeling with Rapid BERT Models. This is a blog essentially around the talk. So you can go over the article, and it covers all of these sections in much more detail. You can check out the custom implementation that I wrote in kubert underscore topic modeling. You can check out the BERT topic library directly, and check out the section on how you can use GPUs to speed up your modeling process. And you can also check out this issue on the topic library on the ongoing discussions we have on accelerating various other parts of the workflow. So the next steps that we are working on is first, just improving HDB scan much more, like introducing soft clustering, introducing and which often the PI actually just merged for that. And then there's other stuff like accelerating prediction and inference, so that when you're actually deploying this model at scale, you also can see the benefits of using a GPU. We're also working on speeding up the algorithm much more on lower dimensions, so that you get much more amount of speed up, because I think we believe that GPUs can offer you much more speed up on the section, and we're working hard on optimizing it. And the other part that we're looking to is figuring out how we can upstream the TF-IDF work into the Word topic library. So yeah, that's it from me. Thanks, guys.